In this lecture, we will be studying power series representations and how you can work with them. So recall, a power series about x equals a is an infinite series of this form. Sum n goes from 0 to infinity of the coefficient c sub n times the quantity x minus a to the n. The first several terms are written out here, and we think of it as an infinite degree polynomial in x minus a. And recall that such a series has an interval of convergence associated with it. First of all, we see that if you plug in x equals a, every term except c0 will be 0. And so this series converges for x equals a. But we have a radius of convergence, r, and the power series will converge on the interval a minus r to a plus r. It will converge absolutely inside the interior of this interval, and then anything can happen at the endpoints. So the key thing to recognize for this lecture is that you have some interval of convergence. It could be just a. You could have a positive and finite radius r, or you could have an infinite radius of convergence r, in which case the interval of convergence is the entire real line. Well, what if on its interval of convergence, the power series converges to some function f of x? So if the series does converges to something, x is involved, so what it converges to should be some function of x. So if we have such a relationship, if there is a function f of x to which our power series converges, we say that this power series is a power series representation of f of x on that interval of convergence. It's another way of writing f of x. It's a different version of the function f of x. You can think of it like a different identity. These two on the interval of convergence are the same thing, but they appear to be different. They're structured differently, but they represent the same function of x. Let's now consider the case, to make things simpler in terms of notation, where a is equal to 0, and consider the case where we have a power series representation for f of x on the interval of convergence I. And we've written out the first few terms here. Then, for all x in that interval of convergence, we can take the derivative of both sides of this equation here. So you have f prime of x on one side, and for the series, we can take the derivative term by term. So taking the derivative of this term using our power rule, Cn is a constant, so that stays out front. Bring the power of n out front, and then reduce the exponent by 1. And we get n Cn to x to the n minus 1. And note that we start the sum at 1 because the first term in our series is c0, which is a constant, and its derivative is 0. Another way you can see this is to take this version of f of x, written this way, and differentiate with respect to x term by term. Derivative of c0 is 0. Derivative of c1x is c1. Derivative of c2x squared, 2c2x. Derivative of c3x cubed, 3c3x squared, so on and so forth. The point being, we can take the derivative term by term of this expression here, f prime of x on the right, term by term differentiation on the left, and that equation, the resulting equation, will hold on our interval of convergence. For example, consider this power series. Sum n goes from 0 to infinity of x to the n. 1 plus x squared plus x cubed, so on and so forth. And when we look at this, we recognize that this is a geometric series with a ratio term of x. Recall, for a geometric series, to get each term, you multiply the previous term by the ratio term. And we see each term is x times the prior term. So, we know that a geometric series converges when the absolute value of r is smaller than 1. In this case, when the absolute value of x is less than 1. So our interval of convergence in this case is the open interval minus 1, 1. We know the endpoints are not included because we know for a geometric series the condition on the absolute value of r is it needs to be strictly less than 1. So we have this interval of convergence for this power series. But we also know that a geometric series, a convergence geometric series, converges to a over 1 minus r. Recall a is the first term in your geometric series. In this case, that's 1. So our series converges to 1 over 1 minus x. Again, because r was equal to x. And this holds for x in the interval minus 1, 1. So we now have a new version of the function 1 over 1 minus x for x in the interval minus 1, 1. Specifically, 1 over 1 minus x equals that sum, n going from 0 to infinity of x to the n, or 1 plus x squared plus x cubed, so on and so forth, for all x in minus 1, 1. We have found a power series representation of the function 1 over 1 minus x for x in this interval. But this means we can take this expression, so this is just rewriting what we concluded on the previous page, and we can take the derivative of both sides, where we differentiate the series term by term. So let's take the derivative with respect to x of 1 over 1 minus x, and we know that will be equal to the derivative of the series, and again here we differentiate term by term, and it will hold for x in the interval minus 1, 1. So let's take the derivative of both sides. Here we have 1 over 1 minus x. We can write that as 1 minus x raised to the negative 1 power. And then on the right, we're taking the derivative term by term. So the derivative of 1 with respect to x, 0. The derivative of x, 1. The derivative of x squared, 2x. The derivative of x cubed, 3x squared. The derivative of x to the fourth, 4x cubed. So on and so forth. And we usually want to write that in summation notation, because writing things in summation notation, the idea is you capture all the terms. Here you're trying to see the pattern, but to write this correctly, you need to write it in the sigma notation, as that represents the entire series. And so it looks like what we have here, we can write this as, and again, if you want, you can just do power rule on x to the n. We have n x to the n minus 1. And then you just have to figure out what's the starting value for the index n. We need the first term to be 1. So if we start at n equals 1, the first term will be, we can check, 1 x to the 0, or 1. When n is 2, we get 2x to the 1, or 2x. When n is 3, 3x squared. So we see we have it correct, and we can write it in sigma notation there. On the left-hand side, we can use our differentiation rules to take the derivative of 1 minus x raised to the minus 1. And we know that from power rule, we'll have minus 1 times 1 minus x to the minus 2 times the derivative of the inside, which is negative 1. The minus 1's multiplied to become 1, and we're left with 1 minus x all to the minus 2. And that's equal to the sum n going from 1 to infinity nx to the n minus 1, or 1 over the quantity 1 minus x squared equals the sum n going from 1 to infinity nx to the n minus 1 for all x in our interval of convergence minus 1, 1. So we have found a power series representation of the function 1 over quantity 1 minus x squared by differentiating this power series that we started with. We can also consider going in the other direction. So the same scenario, we have our power series, and it's a power series representation of f of x on an interval of convergence I. We can take antiderivatives of both sides. So we can have the antiderivative of f of x is the term-by-term antiderivative of the series plus our arbitrary constant c. And so you can see here the summand in our series is nothing more than power rule for integration applied to the summand here. So the constant stays. You increase the exponent by 1 and divide by that new exponent. So you get Cn, x to the n plus 1 divided by n plus 1 plus c. Another way you can see that is if we look at the terms. The antiderivative of c naught with respect to x, c naught x. The antiderivative of c1x with respect to x, c1 x squared over 2. Antiderivative of c2 x squared with respect to x, c2 x cubed over 3, plus an arbitrary constant c. Again, which is kept here. We can draw that over here as well. The key insight here for this theorem is that with this power series representation, you can take the antiderivative of both sides, and for the series, you can take an antiderivative term by term. So if we come back to our previous example, where we had a power series representation for 1 over 1 minus x on minus 1, 1, this geometric series, we can take antiderivatives of both sides. So an antiderivative of 1 over 1 minus x will be antiderivative of this power series, and we can bring the integral inside and anti-differentiate term by term. So if we concentrate on the right-hand side here, there's two ways you can do this. It's really dependent on what you're more comfortable with. We can take the antiderivative of this sum here by saying we have the sum x to the n plus 1 over n plus 1. And you just have to make sure that you start at the right place. And we'll start with 0 for the index. You see if you plug in n equals 0, you get x to the 1 over 1, or just x. So that's your antiderivative of 1. For n equals 1, we get x squared over 2. That's the antiderivative of this term here. X cubed over 3 for the next one, so on and so forth. If you want to write them out term by term and then write the series down, that is fine as well. You can look here and say, okay, antiderivative of 1 is x. Antiderivative of x, x squared over 2. Antiderivative of x squared, x cubed over 3. So on and so forth. And with an antiderivative of both sides, we can put our arbitrary constant on either side. Let's put it over here. Or for now, we can say we still have the antiderivative of 1 over 1 minus x dx. So the right-hand side is done. Let's do the left-hand side, and we'll need a u substitution for that. So let's say u equals 1 minus x. So du dx, taking the derivative of both sides, is minus 1, or du is minus dx. And we can now make this substitution in our integral. So our integral becomes the integral of 1 over u, and our 1 minus x is in the denominator, that's our u. Dx we swap out with minus du. That will be the natural log of the absolute value of u, and we still have this minus sign. So the negative natural log of the absolute value of u plus c. Plugging back in for u, negative natural log of 1 minus x plus c. And we know that that has to be equal to this power series on the right from our theorem. So this is equal to sum n goes from 0 to infinity, x to the n plus 1 over n plus 1, or x plus x squared over 2 plus x cubed over 3, so on and so forth. And we can then note what happens if we plug in x equals 0 and see what we should get for this c. So if we plug in x equals 0, on the left, we will get the natural log, the negative natural log of 1 minus 0, plus c. And on the right, notice when we plug in x equals 0 that every term zeroes out. Natural log of 1 is, of course, 0. And so we get that c is equal to 0. And that gives us a power series representation with the same interval of convergence for the function negative natural log absolute value 1 minus x. And so we have this new way of writing this function, which we achieved via power series integration. And so that really the key take home from this is when you can write a power series, when you have a power series converging to a function on its interval of convergence, you set the function equal to the power series, you can differentiate both sides, or you can anti-differentiate both sides, and the result will hold on the original interval of convergence. This will come in very handy later on when we study Taylor series.